All right, class, welcome to section 1.4, where we will be studying behavior of graphs and rates of change. Okay, so remember, a function is a relation between two quantities. They just simply tell us how the two quantities function relating to each other. So for example, again, functions arise from the need of saying how one quantity depends on another in real life. So for example, we might be analyzing the profits a company is making over time. So this year, this profit, next year, this much profit, and so on and so on. So what we definitely would like to see is what's the trend of the profits this company is making over time. So let's say this might be that graph, and we might again be discussing time versus number of money made in profits. And as we see, the values here are increasing. So the profit's going up, up, up. It's reaching a peak. And then it's starting going down for many years. Yes. Until it's reaching a minimum value. And then things are starting to look up. Not only are they starting to look up, it looks like they're starting to look up faster. So the profit's increasing, but it's increasing faster and faster. So that would be an example, again, of how two quantities are related to each other. So the idea for this section, again, is to look at the graph of a function and tell exactly that. When is a function increasing? When is a function decreasing? And so on. So just as I said in my story, this function is increasing over these years. So when I am looking at when a function is increasing, I'm looking at the corresponding x values. Which years and during which years is the profit increasing, going up, up, up. And also remember, we always looking at a graph from left to right alongside the number line. So we would never look at it backwards. We always look at it from left to right. So as I keep moving to the right, the graph goes up. Same thing. When is this graph coming down? Well, this graph is coming down between these two x values, right? So this is how we will tell our answers. Okay, do not worry much about these notations here. They're a little bit abstract. I copied this out of your textbook. I'm trying to keep things just straightforward. A and B here are random x values, but so don't worry about it. But it kind of goes a little bit hand in hand with what we've discussed in section 1.1, that sometimes we do not need to plug in a number into a function, but maybe a different label, right? A different variable that is discussing, as in this case right here, a random number A and a random number B, okay? So we don't always need to substitute the x's in a function with a number, okay? All right, so we're going to get started with our first example right here. We want to determine where the function is increasing, decreasing, or maybe not going up or down. Maybe the function stays level, horizontal, in other words, constant. Okay, so here it is. I'm going to write this here. Increasing versus decreasing. Okay, here it is. So, first things first, let's look at increasing. Where does the function, again, as we look at it from left to right, where is this function seeming to go up? And that would be right here, okay? So the function is heading up, up, up as we're moving from left to right between these x values. So again, you're going to be reading the x values that make the y go up, up, up. And as you see, it's increasing between an x of -2 and an x of 0. Okay. Decreasing actually everywhere else. So here is the function decreasing. It's coming down, down, down up to this point. And then again, on the right side here, down, down, down all the way. Now we would simply write that functions decreasing all the way from negative infinity up to an x of negative 2. And then again, because this graph slowly but surely is going to go all the way left to negative infinity. So again, which x values make this function come down? So on this whole interval from negative infinity up to negative 2, the y values keep dropping, right? And then remember the union sign we used in 1.2. So again, this stands for union, which simply means the word or. So anywhere between negative infinity and negative 2, or if you're between 0 and infinity, the graph is heading down, down, down. And again, back to infinity, because slowly but surely this graph is heading all the way to the right. So here are the x values that make the y's go down. So let's try this again with a graph that, as you see, at some point is going constant. So I'm going to write increase. So where is this function increasing? Let's keep it at the same color. And the graph does not go all the way down to negative infinity. I want you to see how there's a bubble that starts this graph. So this graph is, first of all, as I move to the right, going up. And let me write that down immediately. So it's increasing between, right here, halfway between negative 2 and negative 4. That'd be negative 3. And it's included because it's bubbled in. And it's increasing up to an x of 0. Okay. Then what happens to this graph is actually not increasing and not decreasing, but staying constant. And it's staying constant between that x of 0 and an x of 3, let's say. And then finally, as you see, this graph is heading back up. So again, increasing, starting at 3 and going all the way right to positive infinity. Okay. So this way, we're really taking care of the whole domain of the function. So we've told you all the way from where the graph starts at negative 3 up until the graph ends at positive infinity, what happens to the graph. It first heads up, then it's staying constant, then it heads up again. Okay. Now, one thing you might notice and might wonder and ask yourselves is about these brackets. So as you see, I have put a parentheses between these switching points. So I don't want to include the 0 at increasing, and I don't want to include the 0 at constant, because at 0 it's switching places, right? Switching from increase. It doesn't belong here or there. Now, I'm not going to count it wrong if you put brackets in between, but most textbooks will always put a parentheses at the switching points. Okay, so that's why I put parentheses, 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 parentheses. I'm putting a bracket at negative 3 because that's the point where the graph starts. So that point is including, it starts right there, and from there on out, it's heading up. But again, at the switching in between values, we put parentheses. Okay. Now, let's incorporate the next piece, which I said I was talking here about a maximum value and a minimum value, okay, which we, of course, don't want to write too much, so we're just going to write max and min. But let's incorporate that in our discussion. So here are a few more graphs for you. And I copied these definitions again out of your textbook. I don't want to go through the whole really definition of it, right? Abstract definition of it. I'm just going to, again, what does it mean for a function to be increasing? We already know means the graph is heading up, decreasing. But here it is. We're talking about maximums and minimums. And if you look at this story here, we have the story about a local maximum and an absolute maximum. And the same thing, we're talking about a local minimum and then an absolute minimum. So I will just simply explain on the graph what they mean. You may read these abstract definitions just fine. But here it is. And by the way, this didn't have arrows, but it meant to have it. As opposed to, as you see this graph here to the right, it actually has these bubbled in ends that were made clear. Okay, so let's one more time. And this time we're going to add on stuff that we've talked about in 1.2, if anything, for review a little bit. I want the domain, I want the range, intervals of increase, decreasing, and then both the local and absolute minimums and maximums. Okay, and let's see how we write that. So let's get started with stuff that we've already discussed. How do I read the domain and the range of a function? Again, I have to look at the graph. How far left and right does this graph stretches, and how far up and down? And as you see, because of these arrows, that means the graph keeps going up, 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 down, 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 all the way to the right and all the way to the left. So both the domain and the range of this function are all real numbers, as these arrows simply suggest the graph is going to go all the way up and to the right and down and to the left. So we're covering everything. Let's go back to the intervals of increase. Where is this function increasing? So it's heading up at first, and then it's heading up on this way as well. So increase, I'll write it down below. Versus decrease. So as you see, it's increasing from negative infinity up to an x of negative 2, and then again from 2 to infinity. So when you're looking at the intervals of increase, negative 1, you do want to read those x coordinates. So all the way up to negative 1, the graph is heading up. And then the graph is heading up again from 2 up to infinity. And in between these two values, in other words, between negative 1 and 2, the graph is decreasing, is falling down. Okay. And as you see, we've covered everything, the whole domain, all the possible x's, going from negative infinity all the way to positive infinity. We've covered everything. The minimums and maximums, let's talk about that. So clearly here is a turning point, and these turning points, we call them local minimums and maximums, and that's a maximum point is a highest point. And this is a local minimum point. So when we head up here at the definition, it says we have a maximum if there is an interval with this number in between. So in other words, if in its neighborhood locally, right, there's an interval left and right of it, all the values left and right of it are lower than this point. So that's what a local maximum means. It's just a point that locally in its neighborhood, as I zoom the graph around it, this is the highest point in its neighborhood as I look left and right. And the same thing, a local min is a point that's the lowest in its neighborhood as I zoom on the graph in on it. Okay. So it's really a local min and a maximum are just turning points in the graph, pretty much. And then what we do with them to say what they are, we give the coordinates. And this has a coordinate of negative 1, positive 1. And the local min has a coordinate of x is 2 and y is negative 3. So we just need to read the coordinates of those points, of those turning points. Okay. I'm going to head down a little bit because it's a similar graph, except for something else is happening in this graph. So we're going to head to this example next. First things first, what is the domain and what is the range? So as you look at this graph right here, again, the arrows suggest the graph is going all the way down, but also all the way left and all the way to the right. Very slowly but surely, the domain, and again, you can write negative infinity to positive infinity if you wish, or you can write all real numbers. We've discussed this in 1.2. So this graph is going to cover the number line for x all the way left and all the way right. The range is different. Again, you can put this on the side, but you will see that the y values covered by it are down from negative infinity, up, up, up. There is, though, a highest point on this graph where it doesn't get any higher than this. So, again, it's kind of hard to make these turning points all fall in a nice corner of the graph. So this one is kind of in between, so I'm just going to say 5.5. I'll put a bracket, we'll just assume that point. And again, if you read it as a 5.4, that's great, or whatever, 5.6, just whatever your best guess is. As I said, it's kind of hard to make these graphs really turn nicely at the corners. Okay. All right, so there it is. Now, this brings me to why I came to this example next. So right here, as you see, I do have a local maximum point. But also, this is not just locally the highest point on the graph as I zoom into it. As I look at the big picture overall, over the whole domain, I see that this is also an absolute maximum. So it's absolutely the highest point that this graph is going to reach. So this has to do also with our range, right? That says no more than 5.5. Okay, so that's what an absolute maximum is for all the highest points, for all the x's in the domain of the function. So it can't get higher than that. Now, as you look at this graph before, there is no absolute min or max. Because this graph keeps heading up, 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 down, 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 down. It's just never going to stop. Okay. So that's what an absolute maximum is. It's just no higher point on the graph than that. And let's just give its coordinates since we added. So the coordinates of this point is going to be, the x is easy to read. It's a 2. The y is this 5.5 that we guessed before. There's the x, and there's the y to it. Okay. By the way, this graph has no absolute min. There's no lowest point on this graph at all. Okay. All right, and then we still need to give the intervals of increase versus decrease. And again, you might want to try that yourselves. Pause the video anytime, try. So here it is, increasing. Are these two pieces of the graph? So in other words, from negative infinity up to this x value, which is -5. And then again, you see the graph is increasing between -2 and +2. And on the rest of it, the graph is decreasing. So it's decreasing in between these values, -5 and -2, and then to the right of 2. So it's decreasing between -5 and -2, and then again from 2 all the way to infinity. Okay. And then I also need to give you the coordinates of these local max. This is just the local. And so its coordinates are -5 for x. And then the y value, let's just say it's 2. It's a little higher than 2, but let's just say 2. And this turning point here is a local min. And its coordinates are x is -2. and y is, I'm going to say, negative 0.5-ish. About halfway between 0 and negative 1. Okay. So again, let's look at this last example, and you might want to pause again and try yourselves. So we are looking for the domain, and remember this graph is going to stop. We're looking for the range. We're looking for the intervals of increase, decrease, and on the graph, put the coordinates of the mins and the maximums. So here it is. The domain is all the possible x values, which, as we see, are only going from negative 9 to positive 5. Okay, that's where the graph starts at negative 9 and stops at 5. It doesn't go anywhere to the right of it. For the range, put the graph sideways and read the possible y values along the y-axis from smallest to largest. And you will see the first point on this graph is as low as 0. The highest point on this graph is as high as 12. So it doesn't go below a y of 0. There's no graph of it. There's no graph below the x-axis, as you see. And then the graph doesn't go past the highest point of 12. That's where we bubbled in. Okay. And let's read the intervals of increase. Let's first go up, up, up to here. Then it's going to head down. And then it looks like the graph is again heading up. And what I'm reading is the x-coordinates of these boundary points. So it's increasing between, I'm starting it at a bracket because that's my first point, so negative 9 up to negative 7. At negative 7 is switching, so that's why I put a parentheses, up to negative 1. And same thing, at negative 1 is switching, and going up all the way to the last possible point, which is 5. And again, I put a bracket because that's the end of the graph right there, and it's included. Now, this point right here is an absolute maximum. It's absolutely the highest point on the graph, and its coordinates are 5 and 12, which is, again, the highest point on the graph. This time we have right here both a local and absolute min. And its coordinates are x is negative 1 and y is 0. So again, that's the lowest point on the graph because that's the range, right? The graph starts at a y of 0 to a highest possible point of y of 12, right? And then I have one more point, and I know you might have questions, but hold on for a minute. This point right here is just a local max. And its coordinates are negative 7 for x and positive 9 for y. Okay. So you probably are wondering, why is this point down here a local minimum as well, but this one up here is just an absolute maximum, and I didn't say local. Local, for local, you need an interval neighborhood around it. So as I look left and right, it's the lowest point in its neighborhood. As I look at left and right, it's the highest point in its neighborhood. There's nothing to the right of this point, of this absolute maximum. So it has no neighborhood around it where this is the highest point around. It is just the highest point coming in from the left. So technically not local. This one's the lowest point in its neighborhood as you look left and right. Same thing with this point. It's nothing. It's not the absolute lowest point, and it's not a local minimum because it doesn't have a neighborhood around it. It just starts right there. Okay, so local is really a turning point in the graph where the graph is switching from increasing to decreasing or decreasing to increasing. Okay, so those are the definitions. Okay, all right, and now I have one more idea for you for this section. It's average rates of change in a function and the difference quotient. So sometimes, again, we're looking at the graph of a function. How do the y values change with respect to the x values? And it might be, again, let's just think about profit over time. And of course, I know time is only positive, so we shouldn't really have anything on the negative axis, but maybe we say the year 2000 is our year zero, so we can definitely look at what happened before year 2000. So if that might be our 0 year, what happens now, and we're looking in the back as the past and ahead as the future. So if I look at the profit of this function over the years, maybe I don't really know what happens here and there, and I just want to know what happens on average between two specific years. So if I just want to know what happens on average between two specific years, all I want to do is go straight up between those 2 points. We call that a secant line. So yes, as you actually see, what happens is that between these 2 years, the profit went up. It actually reached a maximum and started coming down, but maybe we don't exactly have all the details in between. And we're looking at just the raw data at a year before, let's say 2000, the profits were, let's say, right here at a high of 2 million. And then 3 years before the year 2000, let's say at year 3, in the millennium, the profits were at as high as, let's say, 3, so at 3 million. So what we want to know is what happened on average between these 2 years. So if you remember anything about something called a slope, that's exactly actually what we're looking at. The slope of this little line that I drew for you between these two values. But technically, really, what this is a slope is an average rate of change. So I'm just saying that I'm going to use the slope formula, but don't worry if you don't know it. That's what we're looking at is just the idea of average. So what I want to know when I'm looking at average is by how much did the y's change versus by how much did the x's change. So here we read those two coordinates. And then by how much did the y's change? Well, the y's changed from 2 to 3, and that's a change of 1. Yeah, so you simply have to subtract the y coordinates. And then by how much did the x's change? Well, the x's changed from -1 to 3, so 3 minus -1. So that's a change of 1 in y's, and 3 minus -1, be careful, that's a 4. So really, again, if you look at this graph, what does that mean? In the 4 years, let's say, that might be, again, money versus time. So in the 4 years that have passed, the profits went up by 1 million. They actually went up by more than 1 million, but then they started coming down. So remember, we can't quite look exactly at every little detail in between, but we just simply take the raw data. So all I see is that in this year, the profits were 2 million. 4 years later, the profits were 3 million. So our average rate of change went on 1 million over the 4 years. So if you even want, that's a 0.25. So it's, in other words, 250,000 per year, right? Or 250,000 per year on average over the 4 years. Does that make sense? All right, so that's what an average rate of change in a function is. So let's take a specific function here. We do not want to graph it, this 2x squared minus 5. We just want to know what happens on average in this function on this interval. So in other words, I'm giving you an x here, and I'm giving you a second x here. So between these two x values. Okay, so I'm giving you the interval from this year to this year. So I'm giving you the two x values there. All right, so here it is. Now I have the x values. What else do I need? I need the y values. Okay, so how do I find the y's if x's are given? Well, plug them in. And we practiced on that. So f of 2, what happens, what's the y value when x is 2? It's 2 times 2 squared minus 5. So that's, again, order of operation. 4 times 2 is 8. 8 minus 5 is 3. So in other words, when x is 2, y is 3. That's what we found. And here it is. What happens when x is 6? Again, 6 squared, that's 36. Times 2 is 72. And 72 minus 5 is 67. So again, I have the point of coordinates 6 and 67. All right, so to find the average, which we don't really have a notation for, is that we subtract the two y values by how much did the y's change versus by how much did the x's change. And the x's change from a 2 to a 6, and the corresponding y's change from a 3 to a 67. So that's 64 divided by 4, which is 16. Or in other words, 16 over 1. So for every 1 point we go to the right, we go 16 points up. Okay, that's what it means. So let's try this again. Same thing. The 1 and the 5, here are the x values. I need to find the y's to them. So plug in 1 for x. And then plug in 5 for x. You can leave it as 3/5, or you can even take your calculators and change into a decimal, as it might be easier to look at. And then to find the average rate of change, you want to subtract the y's and then subtract the x's. So that's a negative 2.4 divided by 4, which is a negative 0.6. So in other words, the graph of this function is going to go down by 0.6 of a box for every one box we go to the right. Okay, so this graph is actually decreasing, right? Its average rate of change is negative, so that simply means it's dropping in y values, right? So it's going down. And you're welcome to graph this function and see what happens to it between 1 and 5. By the way, if you think about our library of functions from 1.3, this function 3 over x is very similar to 1 over x, so it's heading down. It's our reciprocal function. So between a 1 and a 5, as you see, this graph is decreasing, right? So its average rate of change is negative. So just on a side note. Okay. And finally, again, I kind of have to tell you about the difference quotient as part of the curriculum, but it's really not that important. If any of you are taking this course because you have to move on to business calculus, then definitely that would pop up actually in the first week of classes of that course. But otherwise, it's an abstract, again, definition that it might be a little bit hard to conceptually, because again, you don't see numbers, it's clearly what happened. We know what to do when we plug in a number. We're not plugging in numbers, we're plugging in different x values. And if you remember in 1.1, I was making you plug in an x plus h instead of an x. So here you go, this is y because of this difference quotient. So the idea here, again, is that we are changing our function not from a 1 to a 5, not from a 2 to a 6, but really from some kind of x to some kind of little bit more than x. So we are moving an h distance away between the two x's. What happens to our y values? Well, for any x I'm giving you, to find the y, you plug it in. For any x I'm giving you, to find the y, you plug that number in. So we don't want to tie into specific numbers, again, 1 to 5, 2 to 6. We want to say what happens in general from an x to a little bit more than x, an x plus maybe 1 or an x plus maybe 2 units away. Okay, so that's the idea. So here it is. Let's just practice on a couple problems. So again, how do I find the average rate of change in this function if I'm giving you specific x values? So let's say the x is changing from 1 to 7. So let's try this one more time. Again, when it's changing from 1 to 7, what I still need to find are my y values. So 2 times 7 is 14, minus 5 is 9. So on average, the average change is going from 9 down to -3 versus 7 down to 1. So again, the points here are if x is 1, we found y to be -3. If x is 7, we found y to be 9. So 9 all the way down to -3, that's 12 units. And from 7 to 1, that's 6 units. So here it is. On average, this function is going 2 units up for every one to the right. Now again, here are abstract x values. x1 is just x, and x2 is some x plus h. How do you find the average rate of change? So again, still, it doesn't matter what x values we are asked to plug in. Whether it's a 1 or a 7, to find their y's, I plug those numbers in. Same thing. Now it's asking me to plug in an x. Fine. What is f of x? Well, substitute x with x, it looks the same. Yes. This one might be tricky. Now it says substitute x with x plus h. Okay. So that's 2 times x plus h minus 5. So wherever I see x, I substitute it with 2x plus h. And by the way, this very well simplifies to 2x plus 2h and minus 5. Now to find the average rate of change, we have to do still what? Take the two y values you have and subtract them. Now be very careful here, because I'm not just subtracting a number. Now I'm subtracting a whole expression. So I do need to make sure that I'm distributing the minus sign, that I'm not just subtracting the 2x, but I'm subtracting both the 2x and the -5. So parentheses are really important here to show that we're subtracting all that stuff. So if you properly do the math on it, as in, well, I have 2x plus 2h minus 5, but then I'm subtracting 2x, and here it is. What would be a mistake if we didn't group it? I'm subtracting a negative 5, so that turns into a positive 5. Now in the denominator, I subtracted the 2x values given. So x plus h minus x, what happens to these x values when I combine them? X minus x, 1x minus 1x, that's 0 x's, right? So in fact, they add up to 0 x's, which is nothing, which is also why it was important on the quiz I gave you guys that to recognize that x minus x, yes, is 0 x's, but you don't want to carry it along. That's a 0, and 0 added to anything is just that number. So it doesn't have to be carried along. Now, as you see, again, I have a 2x minus 2x. That's 0 x's. I don't have to write them. I have a negative 5 added to a positive 5. That's also 0. So those are also completely gone because 2h plus 0, that's just 2h. And then when you take the 2h and divide it by h, you get a 2. 2 times a number, like let's say 2 times 3 divided by 3, that's just 2, right? Every time. So here's the last one. Again, on a homework, you'll see I'm only asking you to do this average quotient on a linear function. That's what I would put on a test as well. I'm going to do this one with you. It's a little bit of we call this a quadratic function. It's going to be a little more complicated, but I'm doing this with you, so no problem. So first things first. It says find the average rate of change from 2 to 5. We can do that. So plug in 2, then you'll get a 10. So again, you got the points of coordinates 2, 10. Plug in a 5 into the function. So you get 25 plus 15, that's 40. So the average rate of change is going to be the change in y values over the change in x values. So that's going to be 30 divided by 3, which is 10. Remember also what we talked about, that the fraction line is acting as a grouping symbol. You have to figure out the answer at the top, and then you have to figure out the answer at the bottom. Okay. Now to find the difference quotient, again, if you look back, it simply means to find, again, what happens on this function on the interval from x to a random x plus h, from a random x to a random x plus h. And the h on the bottom simply comes from, again, we're subtracting the difference between the x's is just h, right? X plus h minus x, as we saw it here, is just an h. So our job is to plug these numbers into the function. So what is f of x plus h? Again, it simply means wherever you see x, you write x plus h. Wherever you see x in your function, you write x plus h. Minus f of x looks just like f of x. Okay, so let's do a little bit of algebra on all of this. I'm going to take this aside. That's a common mistake for students to make. So x plus h squared, to square something means to multiply it to itself. Okay. Plus I'll distribute the next one. Be very careful. This one has a minus. That means we need to minus both terms that follow. Okay. So here it is. Let's distribute. X times x, well, that's what the square means. X times h is just that, x times h. I don't know those values. H times x is just that, h times x. And h times h, that's what squares mean. I'm going to distribute the 3. 3 times x is 3 times x, and 3 times h is 3h. So let's see if we have any like terms to combine. I know this has gotten a little massive, but it's not a big deal. So when I look at like terms, again, I see an x squared minus an x squared. And when you, again, subtract a number from itself, that's just going to be a 0. The same thing here. I see a 3x positive and a negative 3x. So 3x minus 3x, that's just 0 x's, which is 0. And then the other like terms I have, by the way, hx and xh are one and the same thing because multiplication's commutative. So it doesn't matter in which order we multiply these terms, they're going to give us the same answer. Now, this is totally fine to leave as an answer, but again, there can be more algebra done to it. Each of these terms are to be divided by an h. So if I take out an h from each one of them, then that's what we're going to be left with. So don't worry, these are skills that we're going to keep practicing in details in the next sections. But yes, this is college algebra. Therefore, this kind of algebra you should already have been able to do and have learned to do. Okay, dividing terms with variables, combining like terms, stuff like that. All right, well, this was your 1.4.